Okay, in the last part of the chapter 3.7, we work with a PT2. Now, don't be confused with my number 13. This was a rather old number. I don't want to change all references to this chapter. So the numbers 11 and 12 are cancelled years ago. So this is PT2 behavior. And this is described in the workbook on 3 pages. See workbook, because this is very important behavior also for closed loop systems, pages 22 to 24. Now there you can find very detailed many properties of the PT2 behavior. You can say this PT2 is that behavior which can explain resonant effects. Yeah, resonant effects. Okay, the first thing is what we should know is the normalized transfer function. There is a K, a DC gain, we will later explain. The K in the numerator, constant factor, but in the denominator, we have then a second order function. This is a second order system. 1 plus P squared. And normally I can use letters, say A and B for the coefficients, but in the PT2 behavior, it is common to write the following expressions to define 2 important parameters. That is 2 times d divided by omega naught, and here we have 1 divided by omega naught squared. In the Laplace table, we often find not the omega naught, which is the resonant frequency, but with a time constant. It's also possible to write the standard form of PT2 in this way. Now then we have the definition of a time constant, of a time function, a time parameter, and you see if you compare both equations, then t is just the inverse of the omega naught frequency. With the names, k is a DC gain. You can see at this transfer function, DC means p is 0, then the result is if p is 0, f, the gain is k. Then we have d, which is the damping factor. We will talk about this damping factor in several typical values later. And omega naught is the natural frequency. Very near to the resonant frequency, but not exactly resonant frequency, the natural radian. Often the word radian is not used here in this name, natural frequency. But of course this is a radian frequency. I want to tell you why this is a very important function in closed loop systems, because many closed loop systems behaves very accurately, exactly like a PT2, or at least they behaves very similar to a PT2, so that the PT2 is a good model of a closed loop system. And if you know many things about a PT2, then this is a helpful knowledge to discuss closed loops in detail. Okay, let's continue with the operation amplifier circuit. Op-amp circuit with resistors, capacitors without inductivities, without an op-amp. See in the student paper page 57. Page 57, just a quick look on this circuit. You see here irgendwie hat mein PDF reader has a problem. Okay, here you see ideal operation amplifier, a capacitor here, a capacitor there. The ratio of both capacitors is N. Here 2 equal resistors, and here a third resistor. The ratio of this resistance value to this resistance value is M. So you need 3 resistors, 2 capacitors, 1 ideal operation amplifier, and this circuit behaves like this PT2, and the ratio together with the 3 unknown parameters K, natural frequency omega naught, and damping factor D, dealing with the component parameters, can be found in these 3 equations. So here you can find the equations. If you know C and R and the ratio values M and N, then with these equations you can calculate the PT2 parameters. If you have given PT2 parameters and you want to know the circuit values, then use these 3 equations. So very quickly, note that the damping factor could also be smaller than 1, and this could have a resonant characteristic without inductivity. Other realizations you can find in the workbook. In the page 24, you see here there is a passive circuit with a resistance, inductivity, capacity. If the voltage over the capacity is related to the input voltage, you get exactly this PT2 behavior. The K is 1, and the natural frequency is calculatable with a square root of the inductivity times capacity. Damping factor depends mainly on the resistance. If a resistance is 0, if you have only LC, you see then you can reach the damping 0 undamped system. But of course, each inductivity has also an internal resistance, so this is impossible to set R to 0. Here you can see a mechanical example for a PT2 system. You have a spring with a spring constant C, a mass with the mass value M, and a damper. If you measure the position at the damper in relation to the position of the spring here, then again you get PT2 behavior, omega naught and D can be calculated with these values. Now this, I think, is a spring mass system you can find in many applications, any car. The connection of the main car with the wheels is done by a spring. The car has a mass, and you need damper to have a good damping of your car, good car characteristic. So in this case you have a spring mass system. So you see the PT2 behavior can be seen very often in real life. So we should know many things about this PT2 behavior to discuss the properties of a PT2. First, have a quick look on a small table where the damping factor is changed over a big scale. If the damping factor is 0, we call this undamped system. Undamped system. If the damping factor is between 0 and 1, then we can say this is a resonant system. A resonant system where the output amplitude could be larger than the input amplitude as resonant frequency, or in this case the step response has an overshoot. In the case D1, that is a special case, we call this critically damped. That is this is a special case. In reality, you cannot reach exactly this one. Normally you are a little bit smaller or larger than 1. If your damping factor is larger than 1, you have to convert this system, into a series connection of 2 PT1 blocks. Yeah. Then you will see there is no overshoot, no resonant effect, just a step response has an exponentially increase to the final value. Not larger 0. Nonsense. Larger 1, of course. If this is equal 1, you can also convert into 2 PT1s. I will give you these equations soon. If damping factor is negative, then you have an unstable system. This starts oscillations without input. That's not so important. The conversion. See workbook page. Let's have a quick look. Quick look into the workbook. The conversion equations you can find on page 23. 23 in the bottom part. And I can show you this conversion. Yeah, note that we have not discussed the step response, and I give you the symbol of the PT2, this oscillating curve of the step response. We have the 3 parameters K, D, and omega naught. And then if damping factor is larger or equal 1, then this can be converted into a series connection of 2 PT1. And for some applications you must convert into 2 PT1s, otherwise you cannot use some equations. So you get a K factor, which is the product of this K factor and this K factor must be the total K factor here. Of course you can put this K factor also in the second block and put here a 1. It doesn't matter because we have a product of functions, and it doesn't matter in which PT1 the K is hidden. You have 2 time constants. 2 time constants, of course, different values, and these can be calculated. T1, T2 is division line. In the denominator, of course, the natural frequency plays a dominant role, and then we have in the numerator an expression d plus and minus, plus 41 minus 42 square root of d squared minus 1. Here you can see this only works if d is larger or equal 1, otherwise this square root, the argument of the square root will becomes negative, and then the time constant is complex, and that is not possible in a PT1. A PT1 must have a real time constant, otherwise this is not a PT1. So this conversion only works if the damping factor is larger than 1, and then with this you can very easily calculate the both time constants. So I show you now the step response. I think the step response, I should copy the part of the workbook into this paper, then I can show you some properties. So you see now the copy of the part of the workbook of the step response. You see here we have 2 expressions. We have one expression which is defined for d smaller than 1, one expression for d larger than 1, and the step response for d equal 1 is missing because really in lab you don't need this anywhere, because either this or that is valid. So of course you can use the Laplace table to get the result for d equal 1, but here I have just skipped this special case, this critically damped case. Okay, if d is smaller than 1, you see output is oscillating. There is a sinusoidal signal with an amplitude. This amplitude is mainly influenced by an exponential function with a negative exponent times t. So this goes down to 0 and you get a final value here. So this is a sinusoidal signal with decreasing amplitude. If d is larger one, you see there is no d and omega naught in this equation, because here you need now the time constants we have calculated by the conversion into 2 PT1. So this is the step response of 2 PT1 blocks. Because if damping factor is larger 1, you cannot use this function, because this is a time function. This must be a real expression. And if d is 1 or larger than 1, this becomes a complex expression, and this is not defined. Okay, the drawing of these both curves can also be seen in the workbook. I have prepared a list of curves in page number 24. Let's have a quick look into this diagram that are produced with my simulation program. You can also use this program, use my simulation program to get these numbers. So I think now we can see the complete curve. Here these curves are produced with the K1 factor. K is 1 for all curves, and the omega naught radiant frequency is also 1 per second. The only parameter which is changed is the damping factor. And here you can see the influence of the damping factor. Here this curve here is calculated with a damping factor 0, and you see the amplitude goes down to 0. The final value is 1 for all curves. Then it goes up to 1, it goes down to 2, back to 0. So this is an oscillation which never ends. So damping factor 0, step response produced a sinusoidal signal which is undamped, which has a constant amplitude. But you see, if the damping factor is 0.1, then the first amplitude goes to 1.7, the second amplitude to 1.4. Here you see, in spite of small damping, the amplitude goes quickly down. And more, the larger the damping factor, the smaller the first overshoot. And you see here there is a special case, 0.7071 is 1 divided by square root 2. Then you have a damping which is very often used in well-damped systems. So the overshoot here is very small and you reach the final value very fast. If damping factor is 1 or 2 or larger, then you see you come into a slow creeping to the final value. So these are the PT2 step responses for different Ds, and I think now you can understand that the damping factor 0, 1 and smaller one, larger one has this type of behavior. I want to show you a very important characteristic point with which we can very quickly estimate the step response, or if you have a measured step response, estimate the damping factor. That is the maximum, the first maximum of this curve. This Tmax point is calculatable, and we have very exact, clear parameters of this first maximum point. I will show you in my paper. Point of first maximum. Note that this point only exists if damping factor is smaller than 1. It is very quickly sketched in this diagram. So we have a final value. The size of the final value is k. That is the unit step response of my PT2. And I show you just this curve, and we can say, okay, this point here, this point has very good mathematical knowledge. We can say, okay, there is a distance between final value and maximum point. We call this delta H. And we have a time from 0 to the first maximum here, which we call Tm. And if we analyze this equation, the first equation here, 6.2, differentiate in respect to t, set this to 0 and solve this equation, then this is really solvable, and the maximum value of my step response of this curve here, d smaller one, is calculatable with the following parameters. That is pi divided by omega naught divided by square root 1 minus d squared. You see, if you know omega naught and damping factor, you can advance with very easy calculation. You can calculate the Tm value very quickly. What also can be done is very important for our control system discussion. That is, delta H is not that what we want to have. We want to have the delta H in reference to a final value k. This delta H over k we called relative overshoot, and I use the letter Ü in Germany. This is das Überschwingen. So this first letter of the German word Überschwingen is a relative overshoot. Relative overshoot. And the good result of mathematical analysis gives the following expression: Ü is just only dependent on damping factor. It is e to the power of, in the exponent we have a minus d times pi, and in the exponent we have a square root 1 minus d squared. So this is very important, because Ü is just only a function of d independent of omega naught. So if we have the overshoot factor, I can find out the damping value. If I have the damping value, I can predict the overshoot factor. So there's a clear relation between those numbers. We can, of course, solve this equation in respect to d. If we do this, it's not so trivial, so you need some intermediate steps. D calculated from overshoot factor Ü is negative natural logarithmic factor. Oh man, Zungenbrecher. Ü divided by a square root function. Who won't believe this can calculate this for yourself. Yeah, if you want to know how can I solve this equation in respect to d, do this. I think you need a quarter of an hour, half an hour, and then you should get exactly this expression. This is a natural logarithmic factor of Ü again, but this is then squared. Okay, so if you know Ü, this is the expression to get d. If you know d, this is the expression to get Ü. And I think I give you some a table with some typical values, d and Ü. If d is 0, Ü is 1. Then the delta H is double the final value. So this is this part is the same size than k, and the Ü is 1. If damping factor is 1, yeah, if you replace here 1, you see this is e to the power of 1 times pi with the minus sign divided by 0, e to the power of negative infinity is 0. So if damping factor reaches the limit value 1, then there is no overshoot. Yeah. Furthermore, if we have a damping factor, for example, of 0.7071, the typical value 1 divided by square root 2, very often an optimal damping, called optimal damping, then the overshoot is 0.04321. Easy to learn. 4.3%. Yeah, then the overshoot looks 4% over the final value, and then this is a very good mechanical damping factor for driving a car, for your car damper, or for instruments which displays measured voltages with an arrow. Then this arrow is also a mechanical PT2 system, and the supplier of these instruments, mechanical measurement instruments, want to have this damping. Then you get a quick display of the measured voltage. Yeah, some other case is, for example, 0.1. If we have 10% overshoot, this has a damping factor. I have to look in my paper. In the student paper, you can read on page 59. This is a damping factor of 0.591. If you want to have only 1% overshoot, the damping must be a little bit larger, then the damping factor is 0.826. Okay, so far the step response has another property, also displayed in a graphical diagram in my workbook. So I just open my workbook again and show you that curve I want to discuss a little bit with you. So this is page 23. Here you see the with my simulation program produced PT2 step response with a small damping. And what you can see, that can be proven mathematically, that if you see here the line for the final value, that the Tmax time, we have a good equation for, from 0 to Tmax, appears again between the cross points of my step response with the final value. The cross point of the curve with the final value, in our case this is K1, the cross point has a difference between both points in time, which is Tn. So this can be proven, and there's not an approximation, but an exact situation. That is also a good knowledge if you stop measurement of a PT2 step response to reconstruct the final value, because you have to find exactly that line which cuts the same distances out of the up and down curve. This is then the final value. And another interesting property appears in the PT2 step response. We have talked about the ratio delta U divided by K. Now, the ratio delta U divided by K is called our factor U. If you calculate the ratio delta U2 divided by delta U1, this is again the same factor U. Delta U3 divided by delta U2 is also U. So the ratio of following up and downs is always U. And with this, you can calculate, for example, the ratio between U3 and U1 is U squared. The ratio of delta U4 to U1 is U to the power of 3, and so on. So in general, we can say if you have very small damping, calculate the ratio between the delta index n divided by delta index 1. This ratio is then u to the power of n minus 1. So this is a good way for very small damping to calculate exact, very accurate values of the damping factor D. Just very interesting curves. In my past, I have really calculated these values, and I want to see this. It's really exact results without any approximations. So far, what can we learn more from a PT2? I think this should be done in the next video.